everyone, welcome to another video. Today we will continue talking about nucleophilic acyl substitution, but we will focus on Fischer esterification, which is a carboxylic acid that goes and forms a product of an ester. This is a little more complicated with a little more steps, and I will try to explain it the best way I can. So first of all, in here you have to locate your nucleophile. Obviously, here you have your oxygen with its lone pair. That is your nucleophile. That will react and attack the carbonyl group of, the carbon of this carbonyl group. Here, what you have to understand and locate is that this carbon, unlike the carbon above of the acid chloride here is very electronegative. It attracts all the electrons, leaving this carbon with a partial positive charge. Plus, the oxygen also attracts the electrons. So this carbon is very electron deficient. In this case, having both oxygens with lone pairs here, there's a resonance structure. There's a resonance here occurring between those two oxygens and this carbon that stabilizes this carbon, making it not as partially charged, and this then makes it a not strong electrophile. So it's not really ready to be attacked here in this case. So this is why here it will still be the electrophile in this reaction, but this is why we need this acid here. This acid will be used to protonate the oxygen of this carbonyl group, which will then increase the positive charge on this carbon. So how this is going to happen is this lone pair here is going to attack this acid, giving us a resonance of this oxygen with the positive charge with another resonance structure here with the positive charge. In this case, when we protonate this oxygen, you can easily see that there is a resonance structure where the carbon is positively charged. In this case, this is a strong nucleophile, and it's ready to be attacked by a potentially weak nucleophile, which in this case, methanol is. So what's going to occur is methanol is going to attack this carbon here. I'll continue on the other page, right here, which is going to give us an intermediate. It's an OH, CH3 with a positive charge, and this H right here. One of the reasons why we moved this double bond here, it's to make place for this one to attack, right? Because if methanol would attack with the carbonyl group having obviously its double bond, then the carbon here would have exceeded its octet, and it's not something we want, right? So in this case, it has a place for another bond, which is why methanol went and attacked carbon. So here we have our intermediate, right? One of the steps in this case, we want to deprotonate this to then give back the lone pair to the oxygen and give him a neutral charge. So in this case, we will use water. What I forgot to say, this whole reaction, because it's not a very strong, and both of these leaving group are almost as equal strength as far as bases wise. This is a two-way reaction, so it's easily reversible. So here in this case, H2O is going to grab the proton, and this is going to go back on the oxygen, giving us H3O+. And now we have a neutral intermediate. Now, in this here, there's a lot of steps. There's a lot of protonation and deprotonation steps. This is why I really like to do, I use my deprotonation, and obviously an H attaches, and we obtain H3O+, which is an acid in this case, right? Which is readily, which wants to give nitrogen, right? And this is why I know in my head that the next step will be to give a nitrogen to one of them, right? But this is, I'll explain why. So here, next step is, the reason why we want to protonate one of these two here is because both of these leaving groups have the same strength. They have the same basicity, so they're both as equal to leave this intermediate. This is why we want to protonate here this hydrogen, well, this alcohol group here, to make it H2O and allow it to leave as water. So what's going to happen is this oxygen is going to attack this hydrogen, giving us with the plus charge. Now I like to redo here. Now this H left, so we're left with water, and then water will be used eventually for something else. Here, we'll go back downstairs here. So now this is ready to leave. This group is ready to leave. So this is going to pop on the oxygen, giving us our close to be final product. And it's water. Now, this water will then be used to deprotonate here, act as a base, to deprotonate and give us our final product, which is the ester product. Then this rolls, recreates the carbon group, and we then obtain our final product of an ester and water. So this is the Fischer esterification. Obviously there is a lot of steps. There's a lot of protonation and deprotonation, but just focus on a few things here. Once you are at this step here, it's really important to locate both possible leaving groups and notice that this possible leaving group, that would be O minus CH3 or OH minus, those are both as equal to leave. Their basicity level is super equal, which is why we need to then protonate here, right? But here we have a charge, so it's easy to figure out that we need to deprotonate for this bond to roll back on the oxygen, giving him a neutral charge. Now that we started deprotonating, we obtain this acid that's ready to protonate. After we protonate, we have the water here, that's a base, that is ready to deprotonate. So this is how I use it, and it kind of makes sense. Every step follows each other, and yeah, so this is how you go from a carboxylic acid that reacts with methanol that needs an acid to then obtain our ester. Thank you, and thank you for watching the video.